All right, we are back with projectile motion. Okay, projectile motion. So, if you remember, projectile motion occurs when a particle or an object is in free fall. Okay, that's the type of motion that an object is when it's in in projectile motion. It's only in free fall, right? That means that the only force acting is gravity. Okay, um, you will see later a little bit that we'll see later that air resistance does have a role to play in it as well, but really most examples that you're going to look at are not going to have air resistance in it. Pretty much 95% of the time it's not going to have air resistance. If it's air resistance, it's basically a whole other problem. You're not really going to use combined air resistance and projectile motion. There would only be acceleration in the negative y direction. Okay. The motion in the x direction is constant velocity. Okay. Okay. So the motion, so in the x direction, right, you're not accelerating at all, even though some people think that you are. You're not. Okay. You're only accelerating in the vertical direction due to gravity. Okay. Here's some equations for projectile motion you need to know. You need to remember your horizontal and your vertical equations. For position, it's x equals vx naught times time plus x naught. Okay. Your your initial x velocity plus your initial position. Okay. Your velocity, whatever your starting velocity is, should be the same as your final x velocity, again, because there's no acceleration. And then you should have a zero acceleration in that direction. Do you notice what I've done here? I just took a derivative with respect to time for all of them. That's what I did. Okay, no tricks about it. That's all I did. Okay, for the vertical direction, you've got 1/2 gt. So this is negative 1/2 gt squared plus vy naught t plus y naught. And I'm making this negative because, again, this is downward. It's a negative y direction, okay? Your velocity is vy equals negative gt, okay, plus vy naught. Again, do you see I'm just taking a derivative here. That's all I'm doing, okay? And then your acceleration in the y direction is just going to be g, or negative g, right? Okay, do you see how that worked out? I just took derivatives. Okay, a ball is launched horizontally, so this is what we call a horizontal launch. Okay, and because it's horizontal launch, that means there's no initial Vy. Okay, so to draw an example of this, right? So here's our elevation. Okay, here's the ball at the top here, and we're gonna shoot it horizontally. Okay, there's our V naught, and we're doing it from a height h. Okay, and what we're going to see is that the ball, when it's launched, is going to go. Okay, it's going to take this parabolic trajectory down, right? It's going to go launch straight to the side, and then it's going to go. Okay, we can derive a couple of things from this, which is great. We need these equations because they're actually shortcuts for a couple things in projectile motion. Okay. The first thing I want to show you here is the time that the ball is a projectile before striking the ground. Okay. The ball is going to be a projectile for a certain amount of time. When it hits the ground, it won't be a projectile anymore. I'm going to start with a position equation. Y equals negative 1/2 gt squared plus vy naught t plus y naught. Okay. And what I want you to recognize is, wait, we said no initial vy. So that middle term with vy naught should just not exist, right? Also, our final height is what? 0? Okay, that should just not exist either. Okay? So what we're going to do instead is when I rewrite this, I'm going to do 0 equals negative 1/2 g, okay? Negative 1/2 g t squared plus y naught. Okay? I'm actually going to rewrite y naught as being h because for height, right? I mean, we're given the height h. We want to derive it in terms of these things. So again, I'm just making sure that I am following the instructions, right? If I used y naught, I wouldn't get credit for that. Okay, and if you take this expression and you get the 1/2 gt on the other side, you end up getting something that looks like h equals 1/2 gt squared. And that's like a general free fall equation, which is really good to know. Okay. Um, and then if you take this and get t by itself, you'll get t squared is equal to um, 2h over g. And then you're not done yet because then you got a square root and you end up getting t is equal to root 2h over g. Okay? I don't know why my camera keeps like wobbling every time I guess I just write really hard maybe. Okay? Even though it's like pinned between my keyboard and my table. Okay? So there's an expression for time. We got it in terms of h and g. There's no v naught in it, but we don't need a v naught in it. Okay. Okay, that's part A. Part B says the horizontal distance traveled by the ball before reaching the ground. Well, horizontal distance is position, right? So x equals vx naught t plus x naught. And wait, but x naught, let's just make that 0 for the sake of simplicity. Okay. So now what I need to do actually is for this value for t right here, I would need to plug in this thing I just derived. So I would have to do x equals v naught times root 2h over g. Okay? And in physics 1, I give this equation instead of x, I use d for distance. Okay? But either one is fine. Okay? The physics 1 kids, they had to linearize that in some of their labs. Okay? Um, Okay, the components of the ball's velocity upon reaching the ground. Well, this one is easy. The x component of velocity is just v naught because, again, it's a perfectly horizontal launch. Now, to figure out the y component, which would be negative gt, and there's no vy naught. Oh, actually, I'll write that in there. Vy naught, but there's no vy naught because it's 0. Okay. Then what we should notice is that, again, t, okay, I'm going to have to use this expression for t again. So I'm just going to plug that stuff in. Vy equals negative g root 2h over g. Okay? Okay. So that's how you get that's vy right there, and then we got vx. Okay, how wonderful. Okay, the speed of the ball upon reaching the ground. Okay, that's a different thing here. Okay, well, in order to find the magnitude of the speed, we just need a Pythagorean theorem, the components, right? So we would have to do vx squared plus vy squared, and all I'm going to do now is just plug in the two parts up here from c that I derived. So that's just going to be root v naught squared plus, okay, vy is going to be this whole thing, negative g root 2h over g squared. And then when you do that, you're going to get root, v naught squared. When you square this, right, you're going to get g squared. Oh wait, sorry. Yeah, you're gonna get g squared times 2h over g. Okay, so then that becomes, g squared 2h over g. And then you should notice, hey, wait a minute. I have a g here. Let's cancel those out. And you end up with an expression for the velocity, which is just root v naught squared plus 2gh. Okay? That's how you get that. Okay. Now, it's important to note that if you launch several objects with the different launch, okay, so different launch speeds, they spend the same time in the air if they're all launched from the same height. Why is that? Why is that the case? So it doesn't matter if you launch the ball really, really fast or really, really slow, it'll spend the same amount of time in the air. Because if you look at the time equation that we derived, okay, root 2h over g, okay, it looks like only height affects, okay, the time an object is in the air, right? I should probably clarify, for Objects launched horizontally. Okay. Very important to clarify. I'm talking strictly about horizontal launch. Okay, that's horizontal launch where you're shooting it like off to the side, strictly for horizontal launch. Okay. Okay. Um, This next example, you can tell I wrote it. I'm a huge fan of Destiny 2. If you don't know what that is, it's a video game. It's really fun. Okay, I've got a Titan PNG right here. I've got Rolk from the Vow of the Disciple raid. Titan is casting Thunder Crash, traveling from point A to G, as shown below. Find the components of the velocity vector at point A, then determine the components of velocity at every other point. Use the fact that each point occurs 1 second after the previous. Also use G equals 10 because we're in the EDZ. If you don't know what the EDZ is, that's the European Dead Zone. It takes place on Earth. That's why I gave you G. Okay. Probably important for me to note that that right. It's on Earth. Right. Okay. So the first thing that I want to do first is we're given that our initial velocity is our initial velocity is 50 meters per second at 37 degrees. Okay, so I need to use my vector knowledge, my trig, to get my components. Okay, my Vx component and my Vy component. Okay, so I'm thinking x component is adjacent to the angle. Do you see that? The x component right here is adjacent to the angle. So I'm going to have to use cosine to get the x component. That's V naught cosine theta. And then the y component right here is opposite the angle. So I'm going to have to use sine to get that one. Okay. And then when I calculate that out, okay, this is going to be 50 times cosine of theta. Cosine of 37 is 4/5. Okay. That's going to give me 40. And then Vy naught is going to be 50 times sine of 37, which is 3/5. And that's going to give you 30 meters per second. Okay. Okay. So now, I'm just going to use, okay, I'm going to use pink for the x component and orange for the y component. Okay. Okay. So at every single point, now here's the fun part. The x component is really easy from here because there's no acceleration. Nothing is changing in the x direction. So it's going to be 40 meters per second everywhere. This is going to be, 40 meters per second, 40 meters per second, 40 meters per second. Do you get the point, right? 40 meters per second, 40 meters per second. You see that, right? Okay, 40 meters per second, and finally 40 meters per second. Okay. Now, the vertical component will change as it goes because there is acceleration. Now, every second, right, g equaling 10, if g equals 10, this means that we lose 10 meters per second each second. Each point takes place 1 second after the previous. So if we start out at 30 meters per second, then at the next point we should reach 20 meters per second because we lose 10 meters per second every second, right? Okay, there's 20. Here's 10 meters per second. Here's 0 meters per second. Here's negative 10 meters per second. Here's negative 20 meters per second. And here's negative 30 meters per second. And I want to point out to you really quickly, okay, that do you notice that with the path being symmetric, that when you're at points on opposite ends of the path, you're going the same magnitude of speed, opposite direction though, right? Do you notice that? Your x component stays constant, but your vertical component, right? You notice how it's flipped on symmetric sides? That's something important for you to know, okay? If a projectile is launched over level ground, so in this example right here, we launch a projectile over level ground, right? This is what we call a ground-to-ground launch. The projectile travels furthest horizontally if the launch angle is 45 degrees. The reason why, now if you go lower than 45 degrees, okay, then what happens is the projectile spends less time in air. Okay? And if you think of the equation x equals Vx naught times t, less t equals less x. Okay? Now, if you go higher than 45 degrees, okay, then you're actually putting more velocity, putting more launch velocity into the y direction. Okay? You're putting less into the x direction. You're putting more velocity into the y direction, less in the x direction. And by that same equation, okay, less, sorry, I guess I should say initial, right? Less Vx initial is less distance, okay? Okay, um, if you have me in class, you know that I'm obsessed with, I saw, what is it called? I saw Alien Romulus one weekend, and I was absolutely freaking out about it because it was an incredible movie. And so I implemented it here. You can barely see Rain Carradine here, who's the main character in that movie, and there's an alien xenomorph. This is like maybe something like you'd get on a biology test where it says like where they'd have like an arrow or something like out here pointing to like right here, and they'd be like identify this part of the cell, right? And you can't see anything because it's just like it's all blacked out. But anyways, so Rain Carradine fires a projectile from y equals 0 at an angle theta with initial velocity v naught. Projectile passes over level ground, reaching maximum height h before striking a xenomorph located at a distance r from the launch point. Total time of flight is t. Projectile starts and lands at the same height. Okay, so I wanted to clarify that, right? Because you know I don't want you to think like, oh well, it's hitting the xenomorph's foot or whatever. Okay, no, it starts and lands at the same height. Okay. I think that's actually a PNG of the Xenomorph Fortnite skin instead of the actual like Xenomorph. Okay, but anyways, the first expression we want to get is t. This is time of flight. Okay. So to get the time of flight, what we can do is we can start with our y position equation. Okay, y equals y naught plus vy naught t minus 1/2 gt squared, and then we can say, okay, wait, but our final launch, our initial and our final launch heights are both going to be 0. Okay. Um, and then so our initial and our final launch heights are going to be 0. Okay, everything else is perfectly fine. Now you've got so let's see, 0 equals vy naught t minus 1/2 g t squared, and you're like, well, okay, well, we have two t's, so we can't really do too much with that. But what we can do instead is if we move the 1/2 gt squared to the other side, okay, now you notice we have t's on opposite sides. We can cancel out, okay, and then we just need to get t by itself. Okay, so you would multiply by 2, divide by g, and you would see that t would be equal to, I'm going to do capital T because it wants us to do capital T. I'm going to do capital T is equal to Vy naught, or sorry, 2 Vy naught over G. Now here's the thing, okay? That's fine, but you got to understand that Vy naught is equivalent to V naught sine theta, right? So the real true expression, the one I really want you to know, is 2 times V naught sine theta over G. Okay? That's the one I really want you to know. Okay, this next one, range equation. Ooh, here we go, range equation. Okay? Range equation, the most important one of all. Okay? Arguably, right? You need to go to prom. Remember the range equation. It'll help you. Okay, we're going to start with x equals vx naught times t. Okay, and you're going to have to see. Okay, I'm going to swap out x for r. Okay, so I'm going to do r equals vx naught. Okay, is actually v naught cosine theta. Okay. And then the t, we're going to use the same time of flight equation I just derived. So I'm going to plug in 2 v naught sine theta over g. Now, one thing to notice, right? This is. I mean, if you remember this is fine. But I think this is the harder one to remember. Okay, I think it's a lot easier to use your trig identities and to actually condense it into something else, and actually condense it a little bit more. Do you recognize that this is the same thing as saying, okay, 2 v naught sine theta times v naught cosine theta. I'm just putting that on the top there. Do you recognize now that first off, there's two things you can do: v naught, v naught. We can condense them into a square, right, by multiplying them together. But you also should recognize that you have 2 sine theta cosine theta. That's a trig identity. That's a trig identity right there. And you end up getting 2. Oh no, you don't need the 2. Sorry. You end up getting v naught squared sine 2 theta over g. And that right there is the range equation as I taught in physics 1. Okay? Okay. And then to get the final part, to derive an expression for h, we're trying to figure out the maximum height of the projectile. I'm going to use the no time equation because I'm going to use the no time equation. You could do it with time if you wanted to. I'm going to do the no time equation though because it's easiest, okay? So I'm going to do vy squared equals vy naught squared. And the reason for this is the easiest is because you can use a very easy relationship here that your final velocity when you get to the height should be 0, right? Because when it gets to the maximum height, your y velocity needs to end up being 0. So 0 equals vy naught, okay, our initial launch velocity. This is v naught sine theta, okay, squared, minus 2g, I'm going to call that h, the height, okay? And then all you got to do is get h by itself, which is pretty straightforward. Okay, you would subtract v naught sine theta squared from both sides and then divide by negative 2g, and you'd end up getting that h is equal to v naught squared sine theta squared over 2g. There you go, height. Okay. And we kind of already talked about this. Which angle maximizes horizontal distance? The angle that maximizes horizontal distance is 45 degrees because that means equal components in x and y direction. And y direction. Okay. So most time in air with most speed. Okay? And then which angle would maximize the height? Well, to maximize the height, it would literally be 90 degrees. And yeah, that's a stupid idea. You don't want to launch your projectile at 90 degrees because that's just straight up. It's not really going to do anything. But then all velocity, okay, would be vertical. So it goes highest. Okay. So then it takes longer for g to cancel that out as you go up. Okay. All right. I believe that's it for projectile. Oh, gosh. No, there's one more. No, there's one more example. Sorry about that. Okay. Last example is launched at an angle off of a cliff, and this one's not too terribly long either. This has Junkrat. I didn't put a Junkrat PNG. I wish I did. Junkrat here is going to fire a explosive with initial speed 150 meters per second and an angle of 53 to the horizontal. So it passes through maximum height at point A, point B, which is the same as height of the cannon. So you see it's goes through A, which is the highest point, B is the same height as the cannon, and then C is where there's a Reinhardt that gets hit by the explosive. Okay, so first and foremost, I need to break this up into components. I need to break this up into components. Actually, let me annotate a couple things here. This height right here is 405 meters. Okay. Okay. So then we need to actually figure out the components of the velocity. Okay. Here's the angle. We're given the angle is 53 degrees. Okay. And this is 150 meters per second. Okay. Can't really see that very well, I don't think. Okay. 150 meters per second. Okay. And then when I'm getting my components here, okay, this is going to be Vy naught, which is V naught sine theta. And then this is going to be Vx naught, which is V naught cosine theta. And when I calculate that out, I end up getting for the y component should be 120 meters per second, and the x component is 90 meters per second. Okay? Okay, so I know the starting place. I just don't know how long it's going to be in the air for. That's the question. I don't know how long it's going to be in the air for. So I know the initial velocities, that's fine. I just don't know how long it's going to be in the air for. So let's figure out how long it's going to be in the air for. I've got y equals y naught plus v y naught t minus 1 half g t squared. I can't just use the time of flight equation because this is not a ground-to-ground launch, okay? It's starting at a height higher than where it is. So what I'm going to do, okay, is our final height should be 0. Our initial height is 405. Our initial y velocity was 120 times t minus 1 half g, which is 5 t squared, okay? I'm using g is equal to 10 because that's just easier, okay? Now, what you should notice, right, is you have this quadratic formula, or this quadratic equation, which you can't really do too much with. Normally you'd have to default to the quadratic formula. However, I'm going to actually make it a lot easier because these are really big numbers. If you notice that all of these are divisible by 5, so if we divide by 5 on both sides, which isn't going to do anything to the 0, if we divide by 5 on both sides, you should end up getting t squared, okay, t squared minus 24t, okay, minus 81. Equals 0. Okay? And that's going to be if you divide by 5 on both sides. Okay? Then you can factor this. You have to figure out, okay, what adds up to get me negative 24 and subtracts, or what adds up to get negative 24 and multiplies to get negative 81? Oh, well, I've got t plus 3 and t minus 27. Okay? And that's equal to 0. So if by factoring, I can figure out that t must be equal to either negative 3 or 27. And now you have to decide, okay, well, which one makes the most sense? And hopefully the one that makes the most sense to you is 27. Why? Because you can't have negative time. You're not going into the past, right? You're not going back into the past. So it should make sense as 27, okay? So where's 27 on all these graphs? It's going to be like right about here-ish. So my graphs shouldn't go past these points right here. Okay, so when I do my graphs, okay, for the x velocity, that's going to be constant. That's going to be 120 all the way. Okay, all the way. That's going to be 120 the whole time. The final y velocity, okay, the y velocity, well, we know that initially we start at 90, okay, which is right here, and then every second we decrease by 10. So I'm going to do, so I start at 90, and then I decrease by 10, and it's just going to look really ugly. I probably am filling this in wrong, but that's okay. It's just really, really hard to see the lines on the graph and how it printed. You get the point, right? You don't really need to do all that. I'm just gonna. Yeah, that's probably way too steep of a slope right there. Shouldn't really be that much, but that's okay. It happens. Okay, all right. That's that. That's projectile motion. All right. See you later.